Work energy theorem. First we'll see for constant force. The statement of work energy theorem is, according to this principle, work done by net force in displacing a body is equal to change in kinetic energy of the body. To prove this statement, we are taking here the object that is mass m, which is moving initially with velocity u. We are applying a force which will produce an acceleration on the body, that is a. So the force is ma, and due to this force the object is displaced in the same direction as the direction of the force. By s distance you can see that the s displacement is there, and after s displacement at point B, the object obtain final velocity, that is v. So here we will see now in this case, as we know from the equation of motion, third equation of motion, v square is equal to u square plus 2as, where v is the final velocity, u is the initial velocity, a is the acceleration, and s is the displacement. Now if we multiply m both the side of the equation, then it will be m v square m u square, and this will be 2mas. Now we'll take this mv square minus mu square. This is equal to 2mas. This 2 will take that side, so it will become half mv square minus half mu square, and that is equal to mas. Half mv square is the kinetic energy, but this is final kinetic energy. We are writing this as kf. Half mu square is the kinetic energy, and this is initial kinetic energy. We are writing this as ki. Here you will see the mass into acceleration, that is equal to force, and this is displacement s. I already told you that the force and the displacement are in the same direction, so theta is equal to 0, and so cos 0 is equal to 1, and so the work done would be force into displacement. That means this force into displacement will write as work done. So you can see here that work done is equal to change in kinetic energy, and this is called the work energy theorem. According to this theorem, the work done by the net force in displacing a body is equal to change in kinetic energy of the body. Work energy theorem for variable force. You will see here the graph in which x-axis we have taken the displacement, and in the y-axis the force. And for the variable force, the object is displaced from xi, that is the initial position, to the final position, that is xf. Here we have divided all this graph into many rectangular strips, and if we are calculate the work done to displace the object from P to S, which is almost the work done for the constant force, and if we'll integrate this from xi to xf, we'll get the work done for the variable force. So as we know, the work done on a body by a variable force F in displacing the body from initial position xi to the final position xf is given by the formula, that is dw is the work done to displace the body the small distance dx here. So we'll integrate it. So dw is equal to force into displacement, and we are integrating this whole work to displace the object from xi to xf, the initial position to the final position. So the integration of dw is w, that is the work done, total work done. And in place of force we can write here that mass into acceleration. If the object is having mass m, and by applying this variable force the acceleration produces a, so it is ma and dx here. But we know that acceleration is given by change in velocity with respect to time, that is for the small change, or you can say for the small time interval if we are taking, that will be equal to dv upon dt. So acceleration can be written as dv upon dt. Further we can write the acceleration as dv upon dx multiply with dx upon dt. You can see very well dx will be cancelled out. So here what we have done, we have taken the derivative of velocity with respect to x position, and then we have taken here the position with respect to the time. Okay, so this way we will differentiate dv upon dt, will write in this way in the differential form. Okay, now we know that dx upon dt, that is change in position, that means the displacement with respect to time, will give us the velocity here v. So we can write in place of dx upon dt, we will write here v, and ultimately we'll get the acceleration is equal to v dv upon dx. Now in equation 1, this is suppose equation 1. In equation 1 we'll put this value of equation 2. So we'll write here by equation 1 and 2, we'll just see that work done w is equal to xi to the xf integration, and in place of acceleration we'll put the value mv dv upon dx, and this is dx here. So w is equal to, this is xi to xf, mv, this is dv upon dx. Dx and dx would be cancelled here, so I'm just cancelling it, and I can write now this work done is m is a constant value that will come out from the integration sign. The integration of the you will see the integration of v will be there, that is dv, v dv, and the integration of v is what? It is from initial position, that is xi to xf we will take. So in this xi, the initial velocity will get here, that is we can write as u, and the final velocity will get here, we can write that v. So here you will see this v is now equal to what? Here as we have changed, look at here, as we have changed here the acceleration as dv upon dx, so if it is changed, the value also changed, that velocity will be from ve vi, or u, you will write u to v, u to v. I'm just writing this u to v only. Okay, that means we are integrating, because we are integrating with respect to dv, so obviously we'll integrate it from u to v. The integration of v is v square upon 2. Now we'll just apply the upper limit and lower limit. You will see the upper limit is v and the lower limit is u. So here the work done w is equal to m, and in place of v we can write here final velocity, that is v square upon 2, and this is m u square upon 2. So the final velocity and the initial velocity, or we can write what? This is half mv square and this is half mu square. So the work done is, this is the kinetic energy, the final kinetic energy, and this is the initial kinetic energy. So once again we'll get here the work done is equal to change in kinetic energy, that is the final kinetic energy minus initial kinetic energy. So change in kinetic energy, and this is only the work energy theorem, that the work done can be measured by the change in kinetic energy, whether the force is constant or the force is variable. Law of conservation of energy. The sum of total energies of all kind in an isolated system remains constant at all time. For example, the sum of kinetic energy and potential energy for vertical motion conserve at every point. You will observe here the example which we have taken, that is, an object is dropped from height h. The mass of the object is m. Initially it is at point A, and the initial velocity of the object is u, which is equal to 0, and this object is dropped from height h. You will see that after some time it is at point B, traveling the distance x, and the velocity will become v1. Then it complete its journey, touch to the ground, that is at the point C. Here the velocity is v2 and the displacement is h. Now we are going to calculate at each point, that is at point A, B and C, the sum of kinetic energy and potential energy will be constant. So to calculate it, first we'll see at point A. At point A, the potential energy is equal to mass, acceleration due to gravity g, and the displacement, that means what is the vertical height, it is h distance from the ground, or it is h height from the ground, so it will be mgh. Now kinetic energy we'll see. As we know, the formula for the kinetic energy is half mv square, but this time the velocity is u square and u is equal to 0, so the kinetic energy will become 0 here. Then we'll see the total energy. Total energy at this point, at the point A, this is equal to E1 and is equal to sum of potential energy plus kinetic energy. You will see E1 is equal to potential energy is mgh and the kinetic energy is 0, so E1 is equal to mgh. Now we'll see at point B. At point B, potential energy is equal to mg, and you will see the vertical height from the ground, that is h minus x. So this is mg h minus x. Now we'll see about the kinetic energy. The kinetic energy is half m v1 square. We are going to calculate v1 here. So for this, the v1 square must be equal to u square plus 2g, and the distance covered here is x, so it is equal to u square plus 2gx. Now u is 0, so simply it is equal to 2gx. We'll put this value of v1 square, that is equal to 2gx, in the value of the kinetic energy. So the kinetic energy, this kinetic energy will become now half m this is 2gx, then 2 would be cancelled here and it will become mgx. Now we'll see the sum of energy, the kinetic energy and the potential energy at point B, and we'll consider this as E2. So this is equal to, the kinetic energy is mgx and the potential energy is mgh minus x. You will find here E2, this is mgx plus mgh minus mgx. So mgx would be cancelled and E2 will become mgh. Now we'll see next at point C, that is at the ground. Here you will find the potential energy because no vertical distance is there, that means it is at the ground only. So according to this we'll say the mgh we are writing, but here mgh is 0, no vertical distance is here, so the potential energy will become 0. Now we'll calculate the kinetic energy. The kinetic energy is half mv2 square, and we can calculate v2 square as u square plus 2g, the vertical distance you will see here, that is means the displacement cover here is h, so it is 2gh here, and u is 0, so it is simply 2gh. Now we'll put the value of v2 square in this kinetic energy formula. The kinetic energy at this point will become now half m v2 square is 2gh, 2 will be cancelled and it will become mgh. Now you will see here, this is the total energy at this point. The total energy at point C, this is equal to E3, consider it. So it is equal to sum of kinetic energy and potential energy. Potential energy is 0 and kinetic energy we have calculated mgh, so E3 is equal to mgh. Now what we have observed, E1, that is the sum of energy at point A, E2, that is the sum of energy at point B, and E3 is the sum of energy at point C, all are equal to mgh. That means it is proven here the sum of energy at each and every point in the vertical displacement will be equal, and this is called the law of conservation of energy. This is called the law of conservation of energy. Okay, that means we have learned the statement before that energy is neither be created nor be destroyed. So here also the same formula you will observe. The initially the kinetic energy, the potential energy is 0 and the kinetic energy is maximum here, sorry, at the point at the maximum height the kinetic energy is maximum, that is mgh, and the potential energy is mgh and the kinetic energy is 0. Okay, now at the point B you will observe the kinetic energy is now the potential energy is converted into the kinetic energy, and at point C the whole potential energy is converted into the whole kinetic energy. So if you just draw the graph between the kinetic energy and the potential energy, that you will observe here in this case that at vertical height you will find the potential energy at the topmost point will be maximum and it will be reduced to 0. it is maximum and it will be reduced to 0. Okay, and if you observe the kinetic energy, you will find that the kinetic energy at this point, that means at the highest point, is 0, but it will be increasing at it come closer to the ground. So what you observe here, this is the potential energy. This is, you will see here, at height h, the potential energy is maximum and it will reduce to 0 to the ground here at the ground. Okay, and what you find, the kinetic energy is increased, you will find here the potential energy will decrease and the kinetic energy will increase. So here you will find the kinetic energy will increase, but at each and every point the sum of these two, means this is the point H, you will find here this is the point H where the kinetic energy, potential energy is maximum and the kinetic energy is 0. This point you can consider as the midpoint. This you can consider at the midpoint where the potential energy and the kinetic energy, the sum of potential energy and kinetic energy is equal to half mgh. Each one is half mgh and the sum of these two will be mgh. Okay, at this point you will find the kinetic energy is maximum, that is mgh, and you will find here the potential energy is 0. Okay, so this is the mgh here and the potential energy is 0 here. Okay, so this way the graph you can obtain. Mass energy equivalence. In the year 1905, Einstein made an incredible discovery that energy can be transformed into mass and mass can be transformed into energy. Before this, we have studied that the law of conservation of mass and the law of conservation of energy, in which we have learned that the mass is neither be created nor destroyed, like that means the mass is always conserved for an isolated body, and the same way we have learned for the energy also, it is neither created nor destroyed. That means energy is always conserved for an isolated body. So energy and mass are separately conserved, but after this discovery we have learned that one can be obtained at the cost of the other. That means the mass can be obtained at the cost of energy, or the energy can be obtained at the cost of mass. That means because the formula given here is the mass energy equivalence relation, that is equal to E mc square, where E is the energy that appears and m is the mass that disappears. That means the m mass which disappears will create the energy E, and c is the velocity of light in vacuum. C is equal to 3 into 10 to the power 8 meter per second. So this is when the mass is converted into energy. The mass, this m mass will be disappear to create E energy. But when energy is converted into mass, by the same formula E is equal to mc square, we can write that mass that appears given as m equal to E upon k square, that is mass, this energy E is converted into mass. That means E energy is disappeared to create m mass. So according to this theory or the quantum physics or the modern physics, the mass and energy are not conserved separately but are conserved as single entity called mass energy. That is the energy that the object possesses even when it is at rest, and simply because it has mass m. Okay, so here this relation tells us about the mass and energy transformation in each other. When M mass is disappear, E energy will create, and if E energy will disappear, M mass will create. And we'll see now the significance of mass energy equivalence. Significance of mass energy equivalence. We know the relation for the mass energy equivalence is E equal to mc square, where E is the energy appear when the M mass is disappear. So is of great significance. In physics, it has solved many unsolved problems, and the law of conservation of mass and law of conservation of energy has been unified into single law of mass energy. For example, the origin of solar energy, nuclear energy from fusion, fission, binding energy of nuclei, etc. have been traced using this relation, because in mass energy relation, c square, that is equal to 3 into 10 to the power 8 the whole square, meter square per second square, or 9 into 10 to the power 16 meter square per second square is very large. Hence, even a small mass difference can produce enormous amount of energy. Most of energy in the universe obtained on account of conversion of mass into energy, like the energy from sun, the energy of any of the stars, all can be explained with this phenomena, the mass energy equivalence. Even we can see the illustration of interconversion of mass and energy in case of annihilation of matter. That means the pair production. You will see when the any of the nuclear phenomena, when any pair production is there, so that time also you will find the mass is converted into energy. So this type of phenomena can be explained by the mass energy equivalence, and it has great significance.